cohomology of algebraic varieties in V.
Okay, thank you. Okay, so a quick recap. So we had X, smooth algebraic variety over K. And last time I took K to be rational numbers. Now let's generalize a little bit and take K with an embedding in C. And we had the algebraic de Rham cohomology, which I'm going to write without any indices to make life easier, is the hypercohomology of X in the sheaf of Caylor differentials. And it's a finite dimensional K vector space. And HnBX will be the simplicial cohomology, or if you like, the dual of the simplicial homology of the complex points of X with coefficients in Q. So this is a finite dimensional Q vector space. And XC is the extension of scalars from K to C via the only map we've got. And we have a comparison isomorphism due to the Grothendieck, which goes from the algebraic de Rham cohomology tensored with C via the map sigma, of course, is isomorphic to the Betti cohomology, which is a Q vector space of finite rank. And this map is given by integration of differential forms over chains. Good. So now a variant which I didn't have time to mention last time. All right, so now I'm going to change notations, which is going to be problematic. So X, now think of X as the complement of a typically normal crossing divisor in a smooth projective variety. So I'm going to call that Y, and I'm very likely to get my X and Y's mixed up. So please watch out for that. So from now on, Y is going to be smooth and projective. And I'm going to take A and B to divisors in Y such that over K as before. And I'm going to take A and B, two sets of divisors, such that their union is a simple normal crossing divisor, and furthermore, that they have no common irreducible components. So, just very quickly, for example, so locally in locally analytic coordinates, if you had local analytic coordinates z1 up to zn on Y, then locally A union B would look something like a product of equations z1 up to zi equals 0.
So A and B are smooth individuals?
Yeah. We can weaken these hypotheses. It's actually not very important. I don't need to take smooth normal crossing, but it doesn't make much difference. So here, a mnemonic, in case I get all my notations mixed up, what X before is really Y minus A. So if I write X instead of Y, please shout out. Okay, so the reason we do this is because I now want to consider relative cohomology. So I'm going to use a slightly non-standard notation. Hn de Rham Y minus A mod B, which is not a great notation, but this is going to be the algebraic de Rham cohomology. You can define it in a very similar way of y minus a relative to b minus b intersection a. So this is a pain to write this down every time, so I'm just going to use this shorthand. And similarly, we can have hn Betty y minus a mod b. This is just notation, yeah. Well, no, it won't be longer. Wait to see what I write now. I could write b minus a, yeah. Well, okay. Yeah, but it won't be this time. Wait and see what happens now. So now it's going to be, if I get this right, by sigma minus a sigma c. See, it's getting longer. Relative. Same thing. This is a complex points, right? So b. I need you to put the sigmas in the right places. C. Okay, so that is longer. Okay, so it's just in a couple of words. Well, you can. The quick way is just with so the open complement you define with the j factorial of a sheaf. That's the quick answer. But intuitively, the relative Betty homology. Homology. You can think of this as closed cycles which have a boundary in B. Okay, hence the notation mod. In the Durham case, you're looking at differential forms. Differential forms on y in the first approximation, modulo exact forms which vanish along B. Okay. Another way to think about, well, there are lots of ways to think about this, but I don't particularly want to write down lots of complexes. So you can just think of this as something that sits in a long exact sequence. It's the cone, yeah, it's the cone of the map. So a differential form on this has a bunch of components such that the restrictions, such that they all map together. The restrictions of this are d's of, yeah. It's easier just to write down definitions than to try and wave hands. It is what it is. So these are closed chains with boundary. And then we also have a comparison isomorphism. Between, so these are also finite dimensional vector spaces over the same fields. And we have a comparison isomorphism y minus a mod b tensor kc isomorphic to mb y minus a mod b tensor qc. Fine. Good. So a quick example. So let's take y equals p1. A equals 0 infinity. B is a pair of points 1, comma y, where y is a rational number bigger than 1. K is q. And then we have this relative cohomology sits in a long exact sequence. So I suggest thinking about it this way in the first instance. Sorry, it'll be gm relative to 1y. Gm H0 1y and H0 Gm. So last time we showed that this gave an explicit complex computing this, and it's spanned by the differential form dx over x. Is that dx? Yep. And this is two connected components, so it's two copies of Q. So this has dimension 2, and we find, H1 Durham of GM relative to 1y dx over x q dx. So this is why I was slightly evasive in the question about relative cohomology, because this always causes a lot of confusion. So I've written this cohomology class as dx.
Sorry, I'm pretty
Yeah.
confused. I mean, you define the relative cohomology, but you don't have anything about, properties of the X.
No.
So,
Well, I do here. I mean, we have.
the first set up.
Yeah, but this uses overfill characteristic. This implicitly uses Fionaca. This is a smooth compactification.
Compactly supported the cohomology and the
It's got nothing to do with this. Forget it. This is all true. These are finite dimensional vector spaces, even just for smooth algebraic varieties. So.
And when you pass to relative, when you don't need some kind of completion. So
The completion is here. Why is smooth projective?
yeah.
This is
With the relative one. Because
no. This all works. It all works fine. Please trust me. Okay, so I was saying here that the different ways of thinking about this relative Durham cohomology. So, and I'm sort of mixing two of them. Dx here is viewed as a one form on GM, but it's as a one form on GM. It's clearly exact. It's d of x, but x as a function does not vanish. The value of x at the point 1 minus the point y is y minus 1, which is non-zero. So it is not exact. As a relative differential form, it's not exact. Okay, so it's a non-trivial relative cohomology class. But strictly speaking, if you were to go through the definitions, what you'd find here is actually something slightly different. You'd find this class comes from here, so it comes from a function that's supported at 1 and y. But I really don't want to get into that. I think it serves more to confuse than anything else. But anyway, clearly this vector space is two-dimensional, and it turns out that you can represent the class which comes from here, which comes from H0, as a one form, which looks like it becomes exact here, but actually it's not an exact form because it's d of something which does not vanish, which is not 0 on a thing. So I hope that clarifies your question. I don't want to go into sort of a rabbit hole. Okay, good. So then the Betti homology is well, I need a complex point. So C star relative to 1y is two-dimensional. It's spanned by the class gamma naught we had last time and a class gamma. So gamma 0 was a loop around 0, and gamma is any path from 1 to y, and clearly its boundary. Gamma 0 is an absolute homology class. It has no boundary. It's a closed cycle, but the boundary of gamma is contained in the points 1, y, so it's a relative homology cycle. Okay, phew. Right, so now, and then the period matrix is what you get when you integrate the basis of differential forms against the cycles. And it's going to be 2 pi I log y 0, and I'm going to get y minus 1 here, which is kind of annoying. So let's rescale this so that we get 1. That's the period matrix of the comparison isomorphism between these rank 2 cohomology groups. Okay, good. So that was the end of the last lecture. And what it's all about is pairing differential forms with cycles, chains of integration. So today, what I want to do is something slightly weird. So I want to pair forms with forms, or duals of forms, something like that. So this is bizarre, but it turns out that it's a lot of very classical constructions are doing exactly that. Good. So everything that I'm going to say works, in fact, for a general, in this general situation. It's a lot more meaningful when the embedding is in the real numbers. But it actually works in the general case. But to make life easier, I'm going to just take the case k equals q. And you can, the details are all in the literature if you're interested. So to make notation even simpler, I'm now going to write m duram so I've triplicated notations, which is very bad style. And I'm going to write mb for now to be this. And the only ingredient is complex conjugation. So because we're over Q, which is a real field, complex conjugation acts on the gives an involution on the complex points of here it is of this, and therefore it gives a map on homology, homology and cohomology, M B MB, and it satisfies f infinity squared is the identity. Okay. So then the idea is just to transport this back to the Duram side. So you can transport this to M Duram via the comparison isomorphism. So we have a diagram. M Duram tends to C. This is the comparison isomorphism. Goes across to M Betty tends to C. That's integration of forms along cycles. Then we can apply complex conjugation to all the cycles. And then go back. Along the inverse of this map, the inverse comparison isomorphism, and that will induce a new map that I want to call S. So S, let me write it here, S is defined to be, it's the map from M Duram tends to C to itself. So it's a comparison isomorphism from Duram cohomology with itself. And it's given by oops. So just copying out the commutative diagram here. That's it. So very quickly, here's a quick analogy, extremely quick because I'm very low on time. You can compare this with a certain notion of p-adic period. So let's go back to the situation of x, for example. Keep my notations light. If x has a good model with respect to the prime p, so and in this case it'll be a smooth normal crossing divisor over zp. Its generic point is the qp points of y minus a mod b. Then you have crystalline cohomology. X. Actually, this is what I want, with Hn. Ugh. And, for example, you can take Monsky-Vashnister cohomology, and there's a lift of Frobenius, which gives an involution on the crystalline cohomology. And this induces a map called Fp on the QP points of, sorry, on the Durham cohomology of X tensored with QP.
Some would argue script X is the corresponding.
Yeah, maybe. Have I done something? Do I want the? Fine. Anyway, the point is that this is an exact analogy of this. You've got Durham going to crystalline, then apply Frobenius and go back to Durham. It's exactly the same thing here, where crystalline is replaced with Betti. You go from Durham to Betti. Now you apply the Frobenius at the infinite prime, which is complex conjugation, and go back. So you can think of this map S as some analog of a p-adic period. So single-valued periods. Let's take omega a class in M Durham and F a dual class in the dual. So you have to suspend disbelief a little bit for what a dual of a differential form, what a dual cohomology class is for now. And what we get is, if you have a class in Durham and class in the dual, then you can send the first one across via the map S and then pair it with the second one. And that gives you a number. So so maybe I should write square brackets here. So this gives us a number. So in reality, because in fact this lands it, you can check easily that this lands in the real numbers. So you assign in this situation, you assign a real number to a pair, to a differential, to a Durham cohomology class and a dual class. And the notation, which is maybe leaves a lot to be desired, is omega, the integral of omega along F. Okay. Yeah, so I'll explain that. It is related to that, but it's actually quite subtle business. So examples. So if if P was the period matrix of the comparison isomorphism that we saw, for example, this period matrix here, P, then we can write PS, I think, is P bar inverse P, which is this is a very, I don't know, this kind of idea goes way back. And it's the matrix of single value periods. So it is to this sort of single valued integration what the period matrix is to ordinary periods. And so that's something very concrete. So let's do some examples. So the example 1 last time, I think, was H1GM. And the period matrix was the 1-by-1 matrix 2 pi I. So applying this formula, we get the single valued period matrix is P bar inverse P, which is 2 pi I bar inverse 2 pi I. And that's just the 1-by-1 matrix minus 1. So the single valued analog of the number 2 pi I is just minus 1. Okay.
Where's dividing those coming from? Dividing those two formulas.
Oh, yeah, maybe I didn't say. So here's the bar and here's the inverse. So P is written in a matrix form. So this is P inverse, and F infinity is essentially the complex conjugate. And the reason is there's a commutative diagram that I didn't write down. But in this, you can replace this with id tensor complex conjugation on coefficients. And so you can push the F infinity into the... You can absorb it into... So multiplying this on the right by F infinity is the same thing as taking its complex conjugate. Is it? Yes, it is. Is it SC linear? Oh, I should know this. I think it is, yeah. Let me think about that. We've agonized over these sorts of questions, and I haven't thought about this in a while, I confess. It's either linear or antilinear. Let me think about that. I think it's C-linear. Yeah, it's C-linear. Sorry, everything's it's C-linear. Yeah, it's obviously C-linear. I'm confused with the case where the field is not. There's some weird thing that happens when the field is not embedded in the real numbers, and you have to really agonize over various different complex conjugates. But in this case, I think it's clear. Yeah. Okay, so the next example too was H1 of an elliptic curve. So I wrote down in a slightly rushed way a 2 by 2 period matrix with periods and quasi-periods. And it satisfied the determinant of P was 2 pi I, which was Legendre's relation. And I said that we write omega 2 is tau omega 1. And now I'm going to, often in the literature you scale things so that omega 1 is just 1, but I'm going to do something different. I'm going to call it lambda 2 pi I. And this lambda is just a bookkeeping parameter. So it's just introducing a new variable, but it's going to keep track of degrees in the Hodge filtration. And that's degrees of modularity is going to be very important. So lambda is just a new parameter I've introduced. And I wrote down some relation which I regret I didn't look it up for this talk, but there was an identity involving, due to Fricke, I think, that involved the quasi-periods in tau, and it involved the Eisenstein series of weight 2. Okay, so what's the single valued period matrix? Well, it's P bar inverse P, and you just plug this stuff in, and you get lambda bar inverse m tau bar lambda bar inverse minus 4 pi m tau lambda inverse lambda bar m tau bar minus 1 over 4 pi m tau. I hope there's no sign there. We can check. And then lambda bar lambda inverse minus m tau, I believe. So I'll now tell you what m is. So m. Oh, so that's an im, yeah. Yeah, that doesn't look. Let me. Yeah, sorry, it's not. Yeah. M and im look similar. They sound similar and they look similar. So M is going to be purple. M is purple and im is white. M of tau bar, yeah. Okay, so what is M? So M is something very... Oh, not yet. So M of tau is minus 8 pi im, so this is im tor, of G2 star tor. So M needs to be in purple. And G2 star is something that's that I always used to think was a bit of a curiosity, but it's very well known. I think this is your notation, Don. G2 tor plus 1 over 8 pi m tor, which is the real analytic Eisenstein series of weight 2. So it's an actually, so Monday I said that the relation between the periods involved G2, which is not a modular form, but this factor here precisely compensates the failure of modularity here, and the whole thing together is in fact a modular form of weight 2. And you can check that oh, sorry. Yes, that's an sorry, I'm rushing a bit. That's an inverse. And the point is that these functions here, maybe I'll say it quickly, they transform in the following way: f of a tor plus b over c tor plus d equals c tor plus d to the r, c tor plus d bar to the s, f of tor, for all A, B, C, D, a 2x2 matrix in SL2Z. And these weights, there's a sort of holomorphic weight R and an anti-holomorphic weight S, and they exactly correspond to these powers of lambda. So im tor has a certain modular transformation law. You read it off from lambda, lambda bar. It tells you that R and S are both minus 1, I believe. And here R and S are both plus 1, plus minus, minus plus. So the point here is that even if you take the most classical example imaginable, just an elliptic curve, and you apply this very, very simple construction, it explains this kind of this definition of this real analytic modular form, which might seem a bit ad hoc, that you've sort of corrected the modularity by this factor. You might not see where it comes from. So 2 things to check, which will be the litmus test, whether I messed this up or not. Yes, exactly. First thing is the determinant is minus 1, because that's the single-valued analog of this equation, the Legendre equation. And the other thing is that the trace should be 0, and it doesn't look good, but I think it's true. And the reason is because this matrix is conjugate to the Frobenius matrix. Well, here, it's obtained from Frobenius by conjugating by a map, and so the determinant and the trace are preserved.
The trace is also not zero. The weights of A and B are different.
I think yeah, maybe there's a lambda in here. I think it should. I think I did this correctly.
Yeah, but the sum of the two and the two diagonal things is also not zero. It's the difference.
Yeah, that's odd. Okay, I'm not going to try and correct it now. I apologize. I think it's correct. It's because Frobenius acts by. I have checked this before, so it should work.
What do you want this square to be identical?
Because what I said it here, because Frobenius, so on, I said this last time, F infinity on M Betty, M Betty is rank 2, and it has an eigenspace. You can decompose it into an eigenspace with respect to Frobenius, and each eigenspace is of dimension 1. So the trace is 0. In this, with respect to this decomposition, the Frobenius looks like this. It has trace 0.
Isn't it the case that the two are conjugate one to the other?
Yeah, something like that.
Traces don't have any
I think lambda is real. Maybe first of all, lambda is real. I think. First of all, lambda is real. No, I'm sure this works. I've checked this many times. Lambda is real. Good point. Okay, I'm digging myself into a hole. I promise you, this has been checked very carefully, so I must have miscopied something. Okay. Okay, I'll fix it for next time. Something odd. Yeah, so there's sorry, I copied these down from my paper, so I'm sure they're full of typos. It's a paper with Clément Dupont. So if someone has internet access, you can maybe look it up now and embarrass me further if it's wrong, if there's a typo in the paper. Clément Dupont, it's called, I think it's called single valued integration and double copy. And it's on the archive. Okay, so, and then one more example was the logarithm, h1 gm1 comma y. Then the period matrix was 2 pi I log y 1 0, and hopefully the single value period matrix is -1 0 log y squared 1. So again, we see the single valued version of 2 pi I is -1, so that's good. And in fact, that example is a degeneration of this one, the elliptic curve case. If you put q equals e to the 2 pi I tau, then I think you get -4 pi im tau, which is essentially ignoring the factors, it's this term. And that's exactly log mod q squared. And so in fact, the third example can in fact be derived from the second example by replacing E with the Tate curve and degenerating towards the cusp. Okay, fine. So the next question is there a formula for this single value pairing? It's very awkward to have to compute the entire period matrix and then have to invert this matrix, and it's complicated business. You'd like a direct formula. So then I'd really like to talk about heights, so I'm going to try to get to that point. So of course we have Poincare duality. Which is the dual of the cohomology of y. So y is smooth projector, if I remind you. This is 2d minus n. Yeah, x wasn't, but y was. Minus d, I think. So d is the dimension of. And there's a generalization of this duality by Verdier to the case of. To the more general case we had, so y minus a mod b, and the dual of this is h 2d minus n. It's the same thing, but you switch b and a. And there's a twist of d. Okay, so theorem from our paper with Clément Dupont. Oh, actually, I have the archive number here, so that's helpful. 07682. So what we do is we take omega to be a section. The theorem is actually more general, but the following situation is sufficient for most of the examples. So we take a global differential form with logarithmic singularities along A. Oops, that's a very narrow A. And we take nu to be the same thing but with singularities along B. So I think here n is the dimension of y, so we're going to take the forms to be equal, of degree equal to the dimension. Oh, well then I'll take D here. I want the degree, I want it to be of middle degree. Sorry, yeah. Yeah, it was correct, but I changed it because there was clearly a psychological preference for calling it D. I renamed it N. Because of this condition on the degree and the dimensions, you get that omega defines a class in Hn not x but y minus a mod b.
Well, are you assuming that y minus a and y minus b is affine?
Yeah, so y is projective and a, y minus a is affine. This could be empty. It would be the empty statement, it wouldn't be interesting. Well, there'd be no form. I mean, I haven't written this. There's no. I haven't written this formula yet. So, yeah, the initial assumptions of the theorem would not hold. So, it's trivially true. And then nu defines. So I'm having to switch all x's to y's and n's to d's in my head as I go along. This is dangerous. So then I'm going to define cohomology classes, and this is equal to the dual so this is now so we have a cohomology class and a dual cohomology class. So the point was that these dual cohomology classes seemed a bit weird, but they can be very concrete we can make them very concrete by invoking this duality. You can view them as forms on a slightly different space.
Sort of invoking a slightly non-trivial fact.
Oh, yeah.
An absolute class there becomes a relative class there.
I am as well, yeah. That's which also relies on the fact that the degree is dimension. Yeah, I'm glossing over quite a few things. The twist will appear. I'll show you the twist in a minute. So the single-valued pairing. Yeah, I did. Don't worry about it. There is a twist, but as sort of Q vector spaces, you can identify their Q structures. And the twist will appear right here. It's the next thing I'm going to write. So it's here. It's 1 over 2 pi I. So in analytic de Rham cohomology, the twist manifests itself as multiplying the form by 2 pi I, but I've got rid of it and put it in the other side of the formula. So that's you're absolutely correct. But we've moved the 2 pi I here for aesthetic reasons. New wedge omega bar. So that's a formula for the single-valued integral. It's a Lebesgue integrable, but it's not a smooth. This is not a smooth form on YC. So you've got to be careful with these integrals. You can't just differentiate under them and apply the usual rules of integration. You get contradictions. It's slightly subtle. And the fact that this integral makes sense at all heavily relies on the fact that we have logarithmic singularities. If you allow higher order poles, this thing is not well defined at all. And as I mentioned last time, there's a whole a couple of papers devoted to this by Kasdan and Felder. It's a very subtle business. Okay, so corollary. So we get the following corollary, which I'm quite fond of, that we call double copy. double copy, which is that nu wedge omega bar. So this is a holomorphic and anti-holomorphic integral. This was the single value period, and the single value period was defined by taking the period matrix inverse complex conjugate and multiplying it by itself. So this is necessarily a period. In fact, it's a quadratic expression in periods. And you can make that explicit so sorry. I need to put a bar somewhere here. Delta bar. Omega. Sorry, nu omega. Okay, so here where this is really multiplying out what it means to be a product of two period matrices. So gamma, respectively, delta is a basis of this relative cohomology. So this is something quite concrete. It's just chains with boundaries contained in chains in Y minus A with boundaries contained in B, respectively with B and A interchanged, and the Čech denotes the dual basis. So what this means is that these dz bar integrals, which are integrals of over domains of dimension 2D, are in fact products of integrals of half the dimension, of ordinary period integrals of dimension D. So in fact these sort of weird single-valued integrals are in fact periods in the classical sense. Right, so now with the there's a sum. You take a sum over a basis. Yeah, I should explain this better. You take a basis of this cohomology and another basis of the other, of the dual one. You sum over the basis, and then this pairing here between these two bases comes from the Betti pairing here.
The Betti pairing depends really on that you have normal cosines for the mean.
But that's the assumption. So that's why in this talk I assumed A and B. I put some quite strong hypotheses on A and B precisely so that I could state this without getting into trouble. Yeah, for D equals 1. I mean, if nu and omega have no singularities at all, this is superclassical. There are special cases which are superclassical. So I'm now going to do the case of heights. That's a very good one. So yeah, okay, so this is a very subtle bit. So if for D equals 1, you allow poles of arbitrary, you're allowed poles of arbitrary degree. The reason is because when you have a point, you can, when you prove this, you can apply Stokes' formula. You can cut little circles around the points and apply Stokes' formula, and you've got Cauchy residue theorem, and that works very nicely. In height,
The two poles can't coincide.
no, they have to be disjoint. So that was another assumption about A and B, that they're far apart. And then you have a little circle of radius epsilon, and then you apply Stokes' formula to this, and you let the epsilons go to 0. And it doesn't depend on anything. In higher dimensions, you can't do this. You want to take naively, you have some divisor and some variety, and you take a tubular neighborhood, an epsilon neighborhood, and you do the same game. But you can't do that because you don't have that tubular neighborhood. So the way KAHW01 and Felder do it is, in one of their papers, they do it in the case of just a single divisor, and they use some very subtle version of the Riemann mapping theorem in families. So your sort of tube could be some horrible thing here, and your forms can massively blow up.
What are they doing?
They're trying to just make sense of, just to define this integral. And it's a really subtle business. So I totally agree. In D equals 1, it's very straightforward, and you can completely drop this logarithmic condition. In higher dimensions, it's a count of ones. Sorry? So this is Frobenius, this is F infinity Yes, their basis of, did I write it? Yeah, Betty here, Betty. So I'm sorry, I'm going a little bit fast. I just been way over ambitious about what I wanted to mention. But I really wanted to mention heights because if you apply this just to a curve, you get the theory of heights. But you get it in a slightly funny way. So since that's one of the conference topics, I desperately wanted to mention this. And I hope I can say something in the time available. So heights. So I'm just going to look at heights on curves. So y is going to be a smooth projective of genus G. And I'm going to fix. We don't have to fix. It's going to be over some fields with an embedding in C, but out of laziness, I'm going to take it over R for technical reasons. But it works fine over C. D in div naught x, a divisor of degree 0. So that's a linear combination of points, linear combination over Z, of points in some in points on Y in some possible extension of K, such that the whole thing is Galois invariant. And then I'm going to say that support of D is contained in A, some subscheme of dimension 0 of Y. So lemma, which is very easy. So there exists a form, a logarithmic form with most logarithmic singularities along A, which is the support of this divisor, such that the residue of this form equals D. But it is only well defined. It is not well defined. It is well defined only up to addition of a holomorphic form, and they are the holomorphic differentials, which I'll give them a name, omega 1 up to omega g. So given a divisor D, you can always find a differential form of the third kind whose residue exactly lines up with that divisor, but that construction is not well defined. Do not confuse with the following statement, which is what you normally see in the theory of heights, which is that there exists a unique nu d sigma. So I'm going to differentiate it from this one by putting a sigma with the same property. So now it has coefficients in C with the property that its residue is D, but it's fixed by a number of possible conditions, but one of them is that it has imaginary periods. So for all gamma closed curves. So if you integrate your form around any closed loop, the periods should be imaginary. So this is not defined over K. I can't emphasize this enough. It's not defined over the field K, so it's not, the height is not obviously motivic in inverted commas. And more precisely, in fact, this form nu d sigma is going to be nu d plus some linear combination of holomorphic differentials, where these numbers here are some weird transcendental numbers. So we had better not use this form to interpret heights as periods. Oh, I think it is sometimes, actually. It's a good question. I mean, in general, clearly not. Actually, we might see in it's precisely to do with vanishing of single-value periods. So yeah, that's a good question. So the definition, I started slightly late, so I'm going to give myself a couple of minutes. The Archimedean height pairing so you take two divisors dE of degree 0, and the definition, so it's a pairing dE sigma, and the definition you usually see in the literature is twice the real part of integral gamma d nu e sigma. So gamma d here is some path whose boundary is the divisor d. So how to explain this? If d is something like sum ni xi, then you could take gamma to be gamma pi. So the gamma is a path from p, some random point to xi. Okay, so this looks like it's a bit sort of single valued because you're taking real and imaginary parts of periods, which is the whole business. And in fact, if you dig around in the literature, you find that the Archimedean height pairing has this nice formula, 1 over 2 pi I integral nu d sigma bar wedge nu e sigma, integrated over the complex points. Again, so this is very classical. But this is not a single valued period. It's not obviously a period at all because these forms are not defined over the field of definition of the curve. Oh, sorry, I've written x here. Sorry about this. Right, so in order to remedy this, it's you have to do something, and this is what I wanted to explain in 2 minutes. So clearly, all this has something to do, the support of the first divisor is in A and the support of the second divisor is in B. This clearly has something to do with M, which is y minus A relative to B. So we're interested in this cohomology group, mixed Hodge structure, and the height's something to do with this. The question is what? So we want to replace these non-algebraic forms with the algebraic versions, nu d and nu e, but nu d and nu e were not well defined. So we can set omega vol to be the wedge product of these forms. Now this is confusing. They're not the actual wedge product of the forms, but the wedge product of the classes. So the meaning of this is the wedge product of the cohomology classes in the exterior power of this this vector space, right? M Duran. And so we look at, so what is the thing we're interested in? We actually want the g plus 1th exterior power of M. That's our motive, if you like. And the differential forms, we want a nu d wedge omega vol, and nu e, this is the algebraic one defined over K, not the transcendental one. And these guys now are, well, if we fix a volume form, which is unique up to some scalar multiple, then in fact these two classes are well defined. So we've got rid of the ambiguity. We've got rid of the ambiguity in nu d and nu e, because so here in this lemma, nu d could be modified by adding a multiple of a holomorphic differential. But when we wedge product with all the differentials, that ambiguity dies. And so these g plus 1 forms are actually well defined as elements of this vector space. So the proposition is that the usual height pairing so it's not a period at all. It's in fact a quotient of periods. More precisely, it's a quotient of polynomials in single-valued periods. So it's the single-valued pairing of these two guys together with nu e and then you divide. So this is ambiguous because the only ambiguity now is this choice of basis fixes this volume form up to overall scalar multiple. But if we divide out by the single value pairing of omega vol, then this thing is completely canonical. So the usual height pairing is in fact this sort of motivic height pairing, which is completely algebraic, just scaled by this volume form. So let me give, in the last 30 seconds, just a quick example for an elliptic curve, and then I'll stop. So if we had an elliptic curve, genus equals 1, there's only one holomorphic differential, which is dx over y in the notations of the previous lecture, and then the Archimedean height pairing for two divisors. If you multiply out this formula and spell it all out, you get minus 1 over 2 pi I. The genuine single-valued integral of forms defined over k, so this is completely algebraically defined, no transcendental coefficients, and then some sign which I don't recall, 1 over 2 pi I integral and you integrate over all the complex points of your elliptic curve, and you need to divide by this volume, which we already computed. It's just the volume of the period lattice. So this quantity here is just minus 4 pi m tau.
If you go over here, omega 1 up to omega g, right, g plus 1.
Yeah, so what this means, so omega I, a class of omega I, is a class in H1 y minus a mod b. So you have an element in a vector space. If you have, a vector space M, and we have V1, Vg, then we can look at the sum, the alternating sum. Maybe I should have written this the first time in wedge G M.
No, that makes perfect sense. So you've written g plus 1.
Ah, sorry.
Okay.
Yeah, sorry about that. Thank you. So then the g plus 1 comes about here because it's this. So what's going on here is that you've got the period matrix of this motive, and you take its single value period matrix, and then you're selecting some minor of it and taking some determinant, and then you divide by a period of this guy, which only doesn't depend on a and b at all. So that's the correct interpretation of a height as a period. Sorry? Well defined. So it means, okay, so it does not depend. So if we fix omega vol, clearly we do, then these forms are well defined. So they do not depend on the choice of differentials of the third kind, which were chosen to have residues along the divisors d and e.
You mean forms, and forms, not just the common type.
Yeah, I mean, it doesn't make much difference. But here, what I mean is cohomology classes. So I'm thinking of a Durham cohomology group with elements in it. So this is an element of that, and this is an element of the dual. So this defines something called a Durham period. So I'll explain that maybe next time. Exactly. So that's what the sort of the theme I mentioned at the end of the last lecture was that a lot of the business with regulators and so on and so forth is the following game, is that you have this period matrix. I don't have one. You have a period matrix, and it depends on a choice of bases. And you ask the question, how do we construct things out of that don't depend on any choices? And this is precisely an illustration of that. First of all, you get rid of choices of paths and so on by making it single valued. It's the first stage. And then you've got to choose, which row and column to pick, and you don't know how to do it because when you choose differential forms, they're ill-defined. But then you get around that by actually taking the big determinant, and the determinant has this property that it kills lots of choices. So this very much illustrates how this whole business of getting well-defined quantities out of period matrices. I'll stop there.
Any questions? Just have a comment that this
Sure.
entire last thing with the heights, both for general G and this formula, are in my paper considered.
Excellent. Oh, this formula is in your paper with conservators?
Well, the whole thing for all G. Yeah, that's
Oh,
actually
excellent.
the paper.
Okay.
I have to tell the story somewhere. And I don't
Oh,
actually
okay,
know
great. So I can, yeah, excellent.
this particular case.
Okay, conservators, thank you. I didn't know that actually. Brilliant. And of course, it goes without saying that the use of heights has spectacular applications in your work and across the board in the theory of L functions and so on.
So, can you analyze this to make really a definition of the actual motivic height?
Well, this is it here. So I haven't defined a Durand motivic period, but this, you could write down, next time I might do this, that your motive is this. That's your motive, and you've got these two framings. So this defines a function on a motivic algorithm or something. And you can check that this guy, Durand period, I haven't defined this yet. This Durand period is bilinear and has all the properties of a height pairing. So this is the motivic height pairing. And you could take its p-adic period and you could do various things with it. But it differs from the usual height pairing by this normalization.
Any other questions?
Sorry for a simple question.
Sure.
How is it, transcendental or S, and this result, is it purely algebraic or?
But the point is to make the definition, the ingredients. Okay, you start with divisors, which are purely algebraic. And the game is to make the defining data completely algebraic, right? But at the end, you have to do integrals. That's always going to be a transcendental operation. So the number you get is transcendental. But the name of the game is to make everything completely algebraic and take something that's incredibly analytic, it's Green's functions and all this stuff that looks incredibly analytic when you see it at first, and interpret it purely algebraically. Because then we can start to think about it from the perspective of all the things we're talking about in this conference. Does that make sense?